Hello, everyone, and welcome back to another explainer. Okay, today we're tackling a total classic in the algorithmic coding world, finding all subsets of a given set of unique integers. Whether you're gearing up for a tough technical interview or you honestly just want to sharpen up your problem-solving skills, mastering this specific concept is a real game changer. It's just one of those foundational problems that elegantly bridges really simple logic with powerful programmatic execution. We're going to visually map exactly how this algorithm thinks, step by step. So let's get focused and crack this problem wide open.
Here is our quick roadmap for today's explainer. 1. Defining the subset problem. 2. The include or exclude choice. 3. Mapping the state space tree. 4. Traversing with backtracking. And 5. Time and space complexity. Let's jump right in.
Section 1. Defining the subset problem. Establishing the goal.
So here's the core question we need to answer. How do we algorithmically find all possible subsets of a given array? Now, a subset can be any combination of the elements, including an absolutely empty set or even the full set itself. The rules here are pretty straightforward. The subsets can be ordered in any way, and we can return them in any order. The real challenge? Just making sure we don't miss a single one.
Now, what's genuinely fascinating here is the sheer scale of the output when you compare it to the input. We're starting with a really tiny, simple array of just 3 numbers, 4, 5, and 6. But look at that output. It explodes into a massive array of 8 distinct subsets. We've got the empty array, individual elements, like just the 4 or just the 5, pairs like 4 and 6, and the entire original array itself. As the input grows even just a little bit, the number of subsets multiplies dramatically. Our algorithm has to be able to systematically generate every single one of these combinations without getting totally lost in the weeds.
Moving on to Section 2, the include or exclude choice, the core epiphany.
So, the absolutely crucial point here is this core intuition. When you look at an array of subsets, it honestly seems pretty complicated at first glance, but the trick to solving it mathematically and programmatically is to just boil it down to a really simple binary choice. For every single number in our input array, we only have to make one decision. Do we include this number in our current subset, or do we exclude it? Yes or no? True or false? That is literally it. Every single subset you could ever possibly create is just a unique combination of those simple yes or no decisions.
Let's actually see that concept in action. Say we want to create the specific subset of 4 and 6 from our original array of 4, 5, and 6. How do we actually build it using our new rule? Well, it's simple. We look at the first number, 4. We choose to include it. We look at the second number, 5. We choose to exclude it. We look at the third number, 6. We choose to include it. By walking sequentially through the array and making that exact binary choice at each and every step, we've perfectly crafted the subset 4, 6.
Section 3, mapping the state space tree, the expanding universe.
All right, we're going to map out what is known as a state space tree. This basically visualizes literally every possible path our algorithm can take. Right up at the very top, the root node, we start with an empty subset. Now, we face our first element in the input array, the number 4. Just like we talked about, our algorithm branches into 2 paths. Down the left branch, we say yes, we decide to include the 4, so our subset becomes an array containing just the number 4. Down the right branch, we say no, we exclude the 4, so our subset stays empty. 1 element down, 2 possible states.
Now watch how fast this builds for our second element, the number 5. We basically repeat that exact same process for the end nodes of our previous step. If we had already included the 4, we now branch again, include 5 to make the subset 4, 5, or exclude 5 to leave it as just 4. Simultaneously, over on the right side of the tree, where our subset was empty, we make that same choice, include 5 to get a subset of just 5, or exclude it to stay empty. Notice how the tree is already doubling in width? With every single new element, our universe of subsets expands exponentially.
Finally, for the third element, the number 6, we just continue branching out for each existing subset from the level above it. Include 6 or exclude 6. Now, focus on that very bottom row of nodes here. After processing all 3 of our elements, we are left with 8 distinct leaf nodes right at the bottom of the tree. And if you look closely, you'll see those bottom nodes match our target output exactly. No way, right? We've successfully generated every single possible subset. By systematically branching our simple yes-no decisions, our tree has naturally discovered the entire solution space.
Section 4, traversing with backtracking, the navigation system. Okay, so one absolutely critical thing missing from the state space tree we just looked at is a way for our algorithm to actually know where it is. Like, how does it know which element of the input array it's currently making a decision on? To solve this, we introduce a tracking variable, an index, which we'll just call I. When I is 0, we're way up at the top, making a decision about the very first element in our array. As we move down a level in the tree, I simply increments by 1. This index acts kind of like our GPS, ensuring we evaluate every single number in our array in the exact right order as we plunge deeper and deeper into the branches.
So how do we actually know when we're done building a specific subset? Well, it happens when our index I equals n, where n is the total length of our input array. If I equals n, it literally means we've made a decision for every single element. We've hit rock bottom of the tree. At that precise moment, the algorithm grabs the current subset we've built and adds a copy of it directly to our final output list. But here's the kicker. The algorithm isn't done. It then uses backtracking. It steps backward up the tree and undoes its last choice. In code, this usually just means popping that last element right out of our current list. Then, it travels down the other branch to explore the rest of the possibilities. It is a wildly efficient, highly organized way of exploring every single path without ever getting stuck or repeating itself.
Section 5. Time and space complexity, the hard truths. Whenever we evaluate algorithms, we've got to look at time and space. The time complexity for finding all subsets is big O of n times 2 to the power of n. Now, why is it so heavy? Because our state space tree has a depth of n elements, and at every single step we have a branching factor of 2. That naturally generates 2 to the power of n total subsets. Furthermore, for every single one of those subsets, we have to make a copy to add it to our final output, which takes big O of n time per copy. But hey, on the flip side, look at the space complexity. It's a highly efficient big O of n, and that's because the maximum depth of our recursion tree, basically how far down into memory we travel at any given moment, is just n. The algorithm only really needs to maintain the current subset data structure, which takes big O of n space. And remember, in standard complexity analysis, we usually ignore the space taken up by the final return array itself. So while it obviously takes a ton of processing time to branch out this massively, it barely takes up any working memory to actually pull it off.
And that, my friends, brings us to the end of our subset journey today. But before we wrap up, I want to leave you with a bit of a provocative thought to test your new understanding. Everything we did today completely relied on an array of unique integers. But what if they weren't unique? How would the state space tree change if our input array contained duplicate numbers, like say 4, 4, and 5? How would you modify your include-exclude decisions to prevent generating duplicate subsets in your final output? Think about how your tree branches might need to be carefully pruned. I really hope this explainer gave you a crystal-clear visual understanding of backtracking. Keep practicing, keep visualizing that tree, and I'll catch you on the next one.